The night sky is a time machine. When we look up, we're seeing light that has traveled across billions of years. It reminds us that our universe had a beginning, and invites the deepest question of all: how will it end? Humans have wondered about endings since we began to wonder at all. We tell stories of apocalypse and rebirth because the unknown is both frightening and fascinating. Modern cosmology doesn't settle for myth, it asks the universe itself for clues. Those clues lead to several competing possibilities, with the last being the most terrifying. The first scenario comes directly from what we observe. In 1998, astronomers measuring distant supernovae discovered that the expansion of the universe is speeding up. Gravity was expected to slow everything down, but instead galaxies are racing apart ever faster. We call the cause dark energy. If dark energy remains constant, it means that over unimaginable timescales the cosmos will expand forever. Picture a roaring campfire. At first it crackles and throws off sparks. As fuel runs out, flames die down. Eventually all that remains are cold, dim embers. In the heat, death, the universe suffers the same fate. Galaxies drift too far apart to see each other. Stars exhaust their fuel. Even black holes evaporate and matter decays. All energy is spread so thin that nothing meaningful happens. A cold, dark sea of particles at maximum entropy. Scientists favor this scenario because it flows directly from current measurements. Dark energy makes up about 70% of the cosmos, and it behaves like a cosmological constant. Unless something changes, the universe simply runs down. What if dark energy isn't constant? Some speculative models allow its strength to increase over time. Cosmologists call this phantom energy. If it exists, the expansion doesn't just continue, it accelerates to a catastrophic degree. Imagine stretching a rubber band. At first it elongates smoothly. Keep pulling and eventually it snaps. Under a big rip, space itself becomes that rubber band. Galaxies are pulled apart. Then the gravitational glue holding stars in orbit unravels. Planets and moons drift free. Eventually, even atoms are torn asunder. The very fabric of space rips everything to shreds. Why consider this nightmare? Because the physics of dark energy is still unknown. Observations so far are consistent with a constant energy, but they do not rule out a component that could vary. Phantom dark energy would violate certain energy conditions, so most scientists view the Big Rip as unlikely. Nevertheless, it reminds us that our ignorance of dark energy leaves room for extreme possibilities. Before the discovery of accelerated expansion, many cosmologists expected that gravity might eventually halt the universe's growth and reverse it. In that case, the cosmos would collapse in a big crunch. Galaxies would fall together, stars would collide, radiation would be compressed to ever hotter energies. An astrophysicist once described compressed starlight cooking the surfaces of stars. The end would mirror the beginning, a dense, hot singularity. The appeal of this idea was that it avoids an eternal cold end. It also emerged naturally from general relativity when the density of matter seemed high enough to overcome expansion. But dark energy changes the balance. With current measurements, a crunch is unlikely unless dark energy somehow switches off or reverses sign. Quantum gravity research offers a twist. Perhaps the crunch doesn't end in a singularity. Instead, extreme densities cause gravity to become repulsive. The universe bounces and begins expanding again, leading to a cyclic universe. This big bounce is like a cosmic heartbeat. Expansion, contraction, rebound, erasing the need for a singular origin and end. It's speculative, but it solves the singularity problem that bothers many physicists. The strangest, and in some ways most disturbing end arises from quantum field theory. The discovery of the Higgs boson confirmed that a Higgs field fills space. Our universe might not be in the most stable possible state of that field. It could be perched in a false vacuum, like a ball resting in a shallow dip on a hillside. If a quantum fluctuation or extreme event nudges the field, it could roll down to a deeper, true vacuum. That roll would create a bubble of true vacuum that expands at nearly the speed of light. Inside this bubble, the laws of physics change. Particles as we know them may not exist. The bubble wall would incinerate everything it touches. Worse, calculations suggest any such bubble would collapse into a black hole. Why take this seriously? Because certain measurements, like the masses of the Higgs and top quark, imply that our vacuum could be metastable. If so, vacuum decay is not forbidden, it's just extremely improbable. The predicted half-life is trillions upon trillions of times longer than the age of the universe. But since quantum tunneling is random, in principle, it could happen at any time, with no warning. The very fact that physics allows such an event illustrates how counterintuitive quantum fields can be. Which of these scenarios will come to pass? If dark energy is a cosmological constant, heat death seems inevitable. If phantom energy lurks, a big rip is possible. If dark energy reverses or new physics emerges, we could collapse and bounce. And if the Higgs field is metastable, a vacuum bubble could obliterate everything. There's deep scientific reasoning behind each. Observational evidence for dark energy's effect, theoretical explorations of dynamical fields, the quest to avoid singularities, quantum field theory's implications for vacuum stability. But these ideas also embody something profoundly human, our need to imagine the unimaginable. We gaze into the cosmos not just to know where we came from, but to guess at our ultimate fate. In asking how the universe ends, we're really confronting how we relate to a world vastly larger than ourselves. Whether the cosmos ends in a whisper, a tear, a crunch, or a quantum blink, the timeline is so immense that life on Earth will have long run its own course. And yet, we ponder the far future with awe. We spin stories out of equations and data. That act of curiosity may be as important as any answer. If you enjoyed this journey into the possible ends of the universe, let us know in the comments, which theory do you find most fascinating? Do you imagine the universe fading into silence, tearing apart in a big rip, or bouncing back to be reborn? If this sparked your curiosity, give the video a like, subscribe to the Space Vault, and continue the adventure with our Big Bang and Beyond playlist, where we explore the birth, life, and future of the cosmos.